All right, let's jump right into a fascinating little chemical mystery. We're talking about a crystal that, well, it basically does a magic trick. It changes color right before your eyes. But of course, it's not magic, right? It's just some really, really cool chemistry.
So just look at this. On the left, you've got this simple yellow powder. You squeeze it, you release the pressure, and boom, it turns this deep, dark green. Then, over on the right, you see that same yellow powder turning green again, but this time all that happened was it lost some water. Two completely different triggers, yet you get the exact same result.
And that right there is our central question. How can a physical squeeze and just, drying it out cause the exact same really stunning transformation? What's the secret sauce that links these two things together? Let's dig in.
Okay, so to solve this little puzzle, first we need to get our terms straight. These two types of color changes aren't just the squeeze one and the water one, they've got proper scientific names. The first one is called piezochromism, that's the change from pressure. And the second is hydrochromism, which, as you might guess, is the one related to water. So let's start with piezochromism. That piezo part comes from a Greek word that means to squeeze. So it's literally squeeze color. It's a color change that happens when you put a solid under mechanical pressure, and this is key, it's reversible. And then you've got hydrochromism. Hydro for water, chromism for color. Easy enough, right? This one is a reversible color change that gets triggered when a material simply dries out or gets wet again. Our little crystal here does both. So what exactly is this stuff?
Well, the molecule at the heart of our mystery is part of a pretty famous family of compounds called viologens. And this is where the story gets really interesting.
Now, for decades, scientists have known exactly what viologens are famous for. You hit them with a little electricity or a flash of light, and they snatch up an extra electron. This turns them into something totally new, a highly colored particle called a radical. It's that radical that gives it the new color.
So here's the kicker. Viologens changing color with electricity and light? That's old news. But changing color from pressure or just from losing water, nobody had ever seen that before. And even more amazing, no one had seen a purely physical force, like a squeeze, cause the exact same electron transfer that electricity and light do. This was like discovering an old, well-known molecule had a secret superpower.
So, how in the world does that work? How does a simple squeeze make an electron literally jump ship from one part of a molecule to another? Well, the answer is actually pretty simple. It all comes down to getting cozy. You're not actually breaking the molecules, you're just cramming them closer together. You force them into each other's personal space. And when they get that close, it suddenly becomes super easy for an electron, that little package of energy, to just hop from one molecule to its neighbor. So let's look at our molecule and see who's giving and who's taking.
So here's our molecule just hanging out in its normal, stable, yellow state. It has two really important parts: an electron donor end that's kind of willing to give up an electron, and an electron acceptor end that wants one. And normally there's a nice, comfortable distance between them.
But now, let's apply some pressure. A lot of pressure, actually. At about 3.6 gigapascals, everything gets squished together. That comfortable distance between the donor on one molecule and the acceptor on its neighbor, it shrinks a lot. They get shoved so close together that an electron just can't resist making the leap. It jumps.
And that's the whole secret. That electron jump creates those colorful radicals we were just talking about. The exact same ones that electricity and light can make, but this time it was triggered by nothing more than a physical force. The result? The crystal first turns red under pressure, and then it settles into that stable green color when the pressure is released.
Okay, so that's a fantastic theory, right? But this is science, and you've got to have proof. How did the researchers know for sure that an electron was jumping and making these radicals? Well, our chemical detectives had to gather some solid evidence.
This was the million-dollar question they had to answer. Was it really radicals, or could it have been something else? They needed a definitive test, something that could only point to one conclusion. They needed a smoking gun.
And here it is. This graph comes from a special technique that's basically a radical detector. Now look at that orange line for the original yellow crystal. It's totally flat, nothing. No signal means no radicals. But then look at the green line for the sample after it was pressurized. Bam! That huge peak is a massive signal. It's an undeniable fingerprint, proving without a doubt that radicals had been created.
And they had other clues to back it up. Other tests showed that a totally new chemical substance was being formed.
X-rays confirmed that the crystal's basic structure wasn't just, collapsing or breaking. No, this was a purely electronic change happening inside a perfectly intact crystal. The evidence was absolutely overwhelming. So let's put it all together. You have these two different effects, piezochromism and hydrochromism. One is triggered by pressure, the other by taking away water molecules. But deep down, they both do the exact same thing. They force those donor and acceptor parts of the molecules closer together, and that makes that critical electron jump happen. The only real difference is how you turn it back. The color from the pressure fades on its own, but the color from drying it out needs a bit of humidity to go back to yellow.
So why is this so important? I mean, a color-changing crystal is cool, but what's the big deal? Well, this discovery isn't just a fun party trick. It actually changes how we think about these materials and what we might be able to do with them.
This is huge. It is the very first time scientists have ever seen an organic material change color from pressure or water loss using this specific electron-swapping mechanism. It proves that a simple physical force can kick off the same kind of deep chemical reaction we used to think needed a jolt of electricity or a blast of light.
And that has some really exciting implications. It gives scientists a whole new tool for designing smart materials. I mean, think about it. You could create tiny sensors that change color to warn you if a bridge is under too much stress, or maybe a simple coating on a package that tells you if it's been exposed to humidity, all by using this simple electron jump. It's like we've unlocked a whole new feature for a classic material.
And that really leaves us with a fascinating final thought. We've just found out that a simple squeeze can be as powerful as a bolt of lightning for starting a chemical reaction. It really makes you wonder, what other amazing materials, what other incredible properties are just sitting out there waiting to be squeezed into existence?